Okay, well, so we'll continue on, and we're still in chapter 7. And we are talking about hypothesis tests. Okay. And so with hypothesis tests, we always form a pair of hypotheses. We always have a null hypothesis and an alternative hypothesis. Oops. Okay, and so the null hypothesis we write and a couple rules is that the null hypothesis always has an equal sign. Okay, so whatever symbols we have in here, there's always going to be an equal sign in the null hypothesis. And that's because when we look at data, the data is always presented in a way so that it can be used to support the alternative hypothesis. The data is never used to try to support the null hypothesis. It's always used to try to support the alternative hypothesis.
That's why the alternative hypothesis is called the research hypothesis.
A lot of times it is, but well, we'll talk about several situations, but and not support the. Let me see. Okay, and yes, in many cases, we set up our hypotheses almost hoping to reject the null hypothesis. This is not always the case, but oftentimes the, quote, more interesting result is when we are able to reject the null hypothesis. So we establish our null hypothesis almost with the hope of rejecting it, okay? But, you know, not necessarily, but you know, I'll say oftentimes. The quote-unquote okay, so we often quote hope and I put hope in quotes there because as researchers we're supposed to be unbiased in our methodology, so we shouldn't try to manipulate any of our results. But usually, when we don't reject the null, it means our data could be a result of random chance or you know, we don't have enough data or things like that. Okay. So again, null hypothesis, we always have an equal sign. So we bring this, let me get this saved here. So we will apply our concepts of a hypothesis test to the t-test, where we are comparing two samples, the means from two samples, to make conclusions about their respective populations. Okay. So the process, again, is we establish our hypotheses, and then we calculate a p-value. Okay, and so do you guys remember what a p-value is?
The probability.
Okay, yes, it's the probability.
Like
It's
being able to
so
like,
it's
have a certain outcome.
and so it's the probability of our data, okay, or of observing our data. So it's always the probability of our data, and we tack on this phrase, or something more extreme, or something more unusual than our data. So the p-value is the probability of observing our data, but it's when we make the assumption, when we assume that the null hypothesis H0 is true. Okay. And so the line of reasoning is for we give the null hypothesis the benefit of the doubt, and we say, okay, well, if we assume that the null hypothesis is indeed true, how likely are we to get the result that we got? Okay. And so if it turns out that our p-value is large, or let's start off with, if the p-value is small, what does that mean? If p-value is...
And it's not really due to random chance.
Yeah, if the p-value is small, that means it is unlikely for us to observe our data when the null hypothesis is true. Okay? And the fact that we did observe this data kind of casts doubt then on the null hypothesis. So if the p-value is small, it means it is unlikely for us to observe our data when the null hypothesis is true. Okay? And the fact that we did observe our data then casts doubt on the null hypothesis. Okay. And on the other hand, if the p-value is large, okay, it means our data could very well happen, or very well be observed, when the null hypothesis is true. Okay? This does not prove that the null hypothesis is true, but it does not cast doubt on the null hypothesis. Okay? Prove that it tells us we do not have enough evidence to reject the null hypothesis. And this is the entire line of thinking for all hypothesis tests. We establish a null hypothesis and an alternative. Our data is always used in support of the alternative. And if it turns out that the probability of observing our data, if we assume that the null hypothesis is true, if that probability is small, then that gives us reason to reject the null hypothesis. And on the other hand, if that probability is not small, then we don't have reason to reject the null hypothesis. Okay? And so in the beginning, we start off with simple t-tests, comparing the means based on two samples. And then we'll do other tests, but they all rely on the same basic setup for hypothesis tests. Okay, so again, this is the classical approach to statistical inference. That's this entire course. But I would say this definition of a p-value is very important. And so if you if ever you're at a dinner party with a statistician, if you can explain what a p-value is, they will be impressed. Not that you're trying to impress statisticians at dinner parties, but perhaps that is kind of it's a significant portion of research done today, for better or worse. P-values have come under some criticism, but maybe because there's an over-reliance upon them. But their original intention and function is quite useful, as a quite useful tool, but perhaps we've become overly reliant. Okay, so let's talk about the t-test. And because we're going to see multiple t-tests, I'm going to specify, and I'll say this is the t-test for comparing means of independent samples. Okay. And we will see some parallels between the t-test for comparing the means of independent samples and the other statistical inference tool that we've used to compare means of samples. And what was that one? That you have already seen. How do we compare the means of samples? We did a confidence interval. Confidence interval for a difference between means, right? And so in that case, the premise is also very similar. You have two samples, and you're looking at the means of those two samples to then make a conclusion about the respective populations. Are the respective populations, do they have the same mean, or do they have different means? Okay. Similar idea here. Okay, except now it's framed in the setting of a t-test. So we start off with a pair of hypotheses. Okay, so our null hypothesis, we write mu1 equal to mu2, or this can also be rewritten as mu1 minus mu2 equals 0. Okay, so both of these things are functionally equivalent, or I shouldn't even say functionally, they are equivalent. They are exactly the same thing, it just may be written in two different ways. And then the alternative, I'm going to use the not equal sign, but also you can have greater than or less than as well. Okay, and again, equivalent to saying that so we could say two things are equal, or that the difference between them is nothing, that there's no difference between two things, or we could say that they're the same. They're saying the same thing. Okay, and let's say we observe data. Okay, data from two independent samples. And so we have sample 1 and sample 2. Okay, so each of these will have a sample size, a sample mean, and a sample standard deviation. Okay, so let's do a simple, I don't know. Okay, we surveyed 15 men and I'll say 17 women. The mean, what shall we measure? Let's say we measure the weight. Okay. Oh, and we'll say the mean weight, I don't know, 184 with a standard deviation of 27. And for the women, we'll say it's 160 with a standard deviation, maybe that's high, I don't know. Standard deviation of 24. I'm making up these numbers. I have no idea. Okay. I don't know what the mean weight of men and women in the United States are, but let's just say this is what we have. Okay, so sample 1 we'll say men USA, and sample 2 also women also USA. Adults, and we're measuring the weight. Okay, and so our question is, does our data provide evidence that the mean weight of all men in USA? Okay, so this would be the mean weight of all men in the USA. This is essentially mu1, right? This is the population mean. Okay. Does our data provide evidence that mu1 is different from the mean weight of all women in the US? Okay, and so this is mu2. Okay, our data being the data that we collected from our two samples, and somehow these were randomly selected. Okay, again, pretty much all of our work is under the assumption of random selection, which again is very difficult to pull off practically, but all of our math falls apart without that assumption. So yeah, it's a little, I don't know, dangerous, I guess, because if you apply these tests and whatnot to data that was not collected randomly, it would be dangerous to then say the conclusions apply to the general population. So you have to think, what could our data be representative of? And that's as far as your conclusion should be generalized to. Okay, so so we have this, and so let's just further explore what our null and alternative hypotheses say. And I'm writing this here because I'm running out of space on my board here, but you don't have to write it here, okay? So the null hypothesis essentially says the mean weight of all men and all women in the population are the same. Okay, so that's essentially what mu1 equals mu2 says. Then the implication is then that the fact that we observed 184 and 155 as the sample means for men and women, the fact that we observed this difference must be a result of the random sampling process alone, okay? Because we are saying the men and the women have the same mean in the population, so whenever we take random samples, we're expecting things to be similar, and the fact that we got something different, 155 versus 184, has to be a result of random chance alone, okay? That we observed samples different means must be a result of random chance alone. Random chance / random sampling, whatever you want to call it. That is what the null hypothesis states. Okay. In contrast, the alternative says, okay, the mean weights of the populations are not necessarily the same, okay? The mean weights of men and women are not the same, and the fact that and we observe different means, different sample means, because of random chance, and also the fact that the population means are different. Okay, and so the question now is, okay, well, 155 versus 184, that's a 29-pound difference. Is that 29-pound difference significant enough for us to conclude that the null hypothesis must be wrong? Okay, so we observe So I'm gonna use this terminology, statistically significant, which is
Alpha.
no, well, okay. So this is the terminology that so many textbooks use, but a lot of statistics educators have complained that this doesn't quite convey the concept here. We just want to know, is this 29-pound difference, is this big enough that it can't be explained by random chance? Okay, that's what this is essentially saying. Okay, so is 29 so big that it can no longer be explained by random chance? Okay. It would be like you send a friend to a grocery store and you give him some money and you say, just bring back the change, buy me a gallon of milk, right? Okay. And if they come back and they said, oh, I spent $5 on a gallon of milk, you'd say, okay, it feels a little expensive, but it's okay, right? That's like grocery stores, they have different prices on gallons of milk, and maybe they bought organic milk or whatever, and so that's fine. But if they said, oh, you know what, the gallon of milk costs $50, you would say, that doesn't sound right, okay? I think you might be lying about the cost of the milk. Okay, and so we do something similar here. We say, okay, because of random chance, we're going to see some fluctuations. Sometimes things on the bigger side, sometimes things on the smaller side. And the question now is, is this number that we get, 29, is that big enough where we no longer believe that it could be a result of random chance alone? That's what we're getting at, okay? Because under random chance, we're expecting things around 0. And we're getting something 29. Is that big or is that small? So we do a little bit of math here, okay? All right. Let's go on. Okay, so now we'll get into the calculation of the p-value. Okay, so the calculation of the p-value, we find something called the test statistic, okay? And the test statistic oftentimes takes on this form of what we observed, okay? How different is that from what we expect based on the null hypothesis? Observed versus expected. Expected based on the null, but oftentimes this based on the null is implicit, so you'll a lot of times see it ignored. And we divide it by what we call the standard error, which is how much fluctuation is I guess acceptable. It's the standard deviation of the sampling distribution, the standard error here. Okay. All right. So from our data on the previous slide, so actually let me flip back here. Copy this. Where do I put this? Okay. Okay, so our standard error is calculated the same way we did for confidence intervals. S1 squared over N1 minus S2 squared over N2. Okay. The observed So let's think back to what our null hypothesis is. Okay, so our null hypothesis, I'm going to write it in this form, is that mu1 minus mu2 is 0. Okay, so under our null hypothesis, we expect, so if null hypothesis is true, we expect y bar 1 minus y bar 2 to be close to 0. So 0 will be our expected, and but what we saw, or what we observe, is y bar 1 minus y bar 2 equal to 184 minus 155. We see a difference of 29. Okay. So let me just plug in all of our numbers for standard error. 27 squared over 15 plus 24 squared over 17. What is this? I'm getting 9.08. .082. Okay, so my test statistic would be my observed difference, 29, minus 0, the expected difference, divided by 9.082. Okay, and for because the t-test for independent samples, difference between means of independent samples, the expected is 0. A lot of times you just see this dropped out of our equations or formulas. Okay, so sometimes you'll see just the test statistic written this way as y bar 1 minus y bar 2, which is our observed difference, right? And then they just leave off the minus 0 because there's no point in having it, and so you see it this way. Okay, but essentially this is the observed difference minus the expected difference of 0 divided by our standard error. Okay, so our test statistic ends up being 29 divided by this thing, and I get a test statistic of 3.193. Okay. So a difference of 29 pounds is 3.193 standard errors away from the mean, and we want to ask, is that significant? Okay. So do you guys have your t-tables with you? Okay, so we're going to have to use that to look up the appropriate area, look up our tail values. Okay, so let's let me pull that out. Okay, so degrees of freedom, how many degrees of freedom do we have? We're going to use the same approximation, n1 plus n2 minus 2. So I have 30 degrees of freedom. So we'll come to our table and we'll use 30 degrees of freedom. And we look at this value, 3.193. Okay? And so we say, okay, in this row for 30 degrees of freedom, where would 3.193 fit? 3.193 fits in between the column that says 2.75 and 3.646. Okay, so 3.193 is in between these two values. Okay, and so that means the corresponding upper tail is then going to be between these two values. .005 and .0005. Is that good with everybody? Okay, so from the t-table, we see that the tail area associated with 3.193 and 30 degrees of freedom is between 0.005 and 0.0005. Okay. All right, so we are tempted to say that this is our probability, our p-value, but it's not. We have to, this is where that phrase, something more extreme, comes into play, okay? So if I put in 0 in the center, we end up at 29 here, and the table says that this area is between 0.005 but more than 0.0005, okay? A difference of 29 pounds apparently is what we're looking at. We would, because our alternative hypothesis, if we flip back a slide, shows not equal rather than greater than or less than, okay? This implies that we would have been interested if the average weight of men was greater than women, but we would have also been interested if the average weight of women was greater than men. So a difference of positive 29 or negative 29 are both equally interesting. And so we would look at the area shaded to the left of negative 29. Okay, and because it's symmetric, we also know that this tail is also between 5 thousandths and 5 10,000ths. Okay. So this is, again, we look at both tails because the key here is because the alternative has a not equal sign, we look at both the positive and negative tails.
Double it.
Yes. So our p-value, our resulting p-value, is thus between 0.005 times 2, so 0.01, and 0.0005 times 2, 0.001. Okay, so we don't know our resulting p-value, but we do know that it's between 1% and 1/10 of 1%. Okay, so this is our p-value. Is this okay? Okay, so let's go back to our original question, which says, does our data provide evidence that the mean weight of all men in the USA is different from the mean weight of all women in the USA? Okay, So our resulting p-value is between 0.1% and 1%. So let's get into what that means. Okay. So our p-value, let me just say, okay, the resulting p-value .001 and 0.01. Okay, or in other words, okay. Let's look at our definition of the p-value again. So I'm going to just write this again. P-value is the probability of observing our data or something more extreme if the null hypothesis were true. Okay, and so once again, our null hypothesis is that mu1 minus mu2 equals 0, or men and women have the same mean weight in the population. Okay, so our p-value is between 0.01, basically 1 in 1,000 and 1 in 100. And so what this says is that if our null hypothesis were true, if men and women truly did have the same mean weight in the population, is it possible for me to get 2 random samples with a difference of 29 pounds from random chance alone? And the answer is yes, it is possible for me to take 2 random samples and get a difference of 29 pounds. But the probability of that happening is less than 1%. It's between 1% and 1/10%. So the question now is, well, do I think it happened? Do I think I'm one of those lucky less than 1%? Do I think I'm in that less than 1% chance? Could that be the case? Or is it more likely that my initial assumption about the means being the same is wrong? Okay. And it's perfectly valid to say, I think I'm one of these lucky 1 in 1,000 people. That's fine, but you know, you have to realize that's a strong claim to make. Okay. It's more likely that our assumptions are wrong. Okay. So what this says is, okay, so interpretation of the p-value here. Okay. It is technically possible for me to take 2 random samples from populations with the same mean and observe a difference of 29 pounds or more. Okay. Okay. The probability of that, however, is quite small. Only between 0.001 and 0.01 chance. Okay, so I would say we will reject our null hypothesis. Okay, so I am willing to reject the null hypothesis and conclude that the mean weight mean weights of men and women in the population are different. Okay. Alternative. Yes. Yes. So that is correct. I reject the null and I accept that the alternative is true. I could be wrong though. And what's the probability that I'm wrong?
0.1?
Yeah, between between 1% and 0.1%. Okay. Well, according to the laws of probability. Yes.
Is the test statistic always supposed to be positive?
No, it could be negative. Okay.
And you just do the absolute value for the...
Yeah, so when you look up your test statistic in the table, just use the absolute value because it's symmetric. Okay, so it's symmetric, so just if you get a negative test statistic, you look it up in the table and just change it from upper tail probability at the top to lower tail probability. But it's the same. It's the same because it's symmetric. Okay, so but let me just write this. I could be wrong. And the probability that I'm wrong
It's like flipping a coin 10 times and having them all come up tails, and chances are...
Yeah. So if somebody flips a coin 10 times and they get tails all 10 times, you could conclude, wow, that guy was really lucky, 1 in 1,000 chance. Or you could conclude he must be doing something funny so that so the coin lands tails more often than it should. Okay, and I guess your conclusion there. So strictly from a classical statistics perspective, we would just say, well, the probability of this happening by random chance is so small, we're going to conclude that he must be doing something fishy. Okay. I guess in a Bayesian sense, you would take into account other information that you might know. All right, so let's talk about this significance value. Okay, so our decision to reject the null or not reject the null. These are the only two conclusions we can make. Depend on the resulting p-value and kind of an arbitrary line in the sand, which we call a significance level. Arbitrary value. Okay, and so the significance level, known as alpha, okay, is what will decide whether our p-value is small enough for us to reject the null, or if the p-value is not small enough, or p-value is too big, that we do not reject the null. Okay, so if our p-value is less than alpha, we reject the null. Okay, and over time and I don't know, because of tradition or whatever you want to call it, the most commonly used value of alpha is 5%. And if it, so if the p-value is less than 5%, we reject the null, and if it's greater than or equal to 5%, we do not reject the null. That's just kind of been established over time, but as the researcher, you get to pick your significance level. And if you want to use significance level of 1%, you can. If you want to use significance level of 10%, you can. Generally, any value between 1 and 10% is probably acceptable. Although a lot of journals kind of expect 5% or less. Okay. So, but you know, is acceptable with but you know, if nothing is specified, you can kind of go under the assumption that alpha is 5%. Okay, so this is the default value. Okay, and so our significance level alpha also it suggests our willingness to be wrong about the null hypothesis. So if alpha is equal to 5%, how often will we reject the null when the null is true, when our data actually was just a result of random chance? 5% of the time. Okay, so if our decision criteria is that, you know, if our formula says that this happens less than 5% of the time, we're then going to reject it, then that means 5% of the time we're going to be rejecting the null hypothesis even when the data was a result of random chance. We just happened to get one of those kind of slightly unusual samples. Okay? So with alpha equal to 0.05, we will mistakenly reject the null hypothesis even if our data was purely a result of random chance. % of the time. Okay, and so this mistake, this is known as a type 1 error. Okay, this is a type 1 error. This is rejecting the null when in reality the null hypothesis is true. Okay. So we can also write probability of a type 1 error is equal to alpha. And so our choice of alpha reflects kind of our willingness to make a type 1 error. So we are saying I'm willing to live with making a type 1 error 5% of the time when I say alpha is 5%. So our choice okay. And we don't want to make errors, okay? We don't want to reject the null when the null is true, okay? So ideally, whenever the null is true, we don't reject it, and when the null is false, we do reject it. So we don't want to be making too many errors. So you might ask, well, why don't we just crank down alpha to be really small, okay? Then we would be making type 1 errors a lot less often. Okay, well, the flip side to a type 1 error is creatively named the type 2 error. And the type 2 error is kind of the opposite problem. So if type 1 error is rejecting the null when the null is true, can you think of what the type 2 error is?
Accepting it when it's false.
It's not rejecting the null when the null is false. Okay, so I'm being nitpicky here, but we should never say we accept the null. Okay, and I'll explain that in a little bit. But yes, so type 2 error is just the flip side where our decision is not to reject the null, but the null is actually false. Okay, so that is And so by decreasing alpha, if we decrease alpha, we are inherently going to increase the probability of a type 2 error. Because decreasing alpha means you are rejecting less often. Okay? And by rejecting less often, you are thus increasing your risk that you didn't reject when you should have rejected.
Isn't alpha also a probability value?
Yes, so alpha is the probability of a type 1 error. It's our significance level. And we get to choose that. Okay, and so let me see. Okay, so decreasing alpha inherently increases the risk of type 2 error. Okay. And so the probability of type 2 error, we give the Greek letter beta. So alpha is the first letter of the Greek alphabet, and beta is the second letter. So that's what we have. Okay, so type 1 error is rejecting when the null is true. Type 2 is not rejecting when the null is false. And so decreasing alpha increases the risk of type 2 error, or decreasing alpha increases beta. Okay. The complement to a type 2 error, we give a special name, or actually, so power is equal to 1 minus beta, which is the probability of the complement to a type 2 error. And this is the probability of correctly rejecting the null when the null is false. And this is a good thing. If the null hypothesis is false, we want to reject the null hypothesis. And so so that's power. Okay. That's maybe in medical tests, this is also known as the sensitivity of a test, meaning if you've got a disease, how good is this test at picking up the disease? That's the sensitivity of a test. And the opposite of alpha would be the specificity of the test, meaning we don't want to have a bunch of false alarms, right? Okay, and so I think, part of the reason why, so null hypothesis testing, significance testing, as we call it, this hypothesis testing stuff, it's a very useful tool, and it forms kind of the basis for t-tests, and as we do ANOVA and chi-square tests and all of that, it's very useful and it's very good. It's come under a lot of criticism lately, and I think it's because a lot of people kind of apply these tests without doing a lot of thinking or critical thinking behind it, and we just kind of throw the data at the computer, say spit out a result, this computer spits out this p-value, and we get p-value 0.08, and we say, bah, it's not significant, or p-value 0.02, it's significant, and we go off of that. And I think as researchers, we should be conscious of when do we want a large alpha, when do we want a small alpha, and things like that. So I'm gonna give us two very not silly examples, but just situations where In one, we might want a large alpha, and in one, we might want a small alpha. Okay, so imagine a smoke detector. Okay, and you install a smoke detector to inform you of when there's a fire. Right? This is the purpose of having a smoke detector, and so when you start the smoke detector, it starts off with the assumption that it starts off with a null assumption or null hypothesis. It assumes that's true until enough data or evidence comes by to reject that. Okay? So with the smoke detector, one of the hypotheses will be there is no fire, and the other one is that there is a fire. And which one is the null and which one's the alternative?
There is a fire is the null.
I would argue just the opposite. I would say the null hypothesis, it's going to assume that the null hypothesis is true until there's evidence to reject that. So the null hypothesis would be that there is no fire, and the alternative is that there is a fire. Okay, and basically if enough smoke goes past its sensors, it's going to reject the null and say this amount of smoke cannot, or this amount of whatever, it detects particles, right? And it says this amount of particles can't be explained just by dust blowing in the air. This must mean something's generating smoke, and I'm going to sound an alarm. Okay. So in this case, what would so let me just list off correct operation. There are two correct operations. Correct operation is sound the alarm when there is a fire. And the other correct operation, what is the other correct operation? Yeah, don't sound the alarm when there is no fire, okay? Okay, and there are two ways the smoke detector can fail or not operate correctly. Okay, and what is one of those?
The sound an alarm when there is no fire.
Okay, sound alarm when there is no fire.
Don't sound an alarm when there is a fire.
And the other is don't sound the alarm when there is a fire. These are both malfunctions or not behaving the way it should be, okay? Okay, so which one is the type 1 and which one is the type 2 error? So type 1 is rejecting the null when the null is true, and type 2 is not rejecting the null when the null is false. Yeah, sounding the alarm when there is no fire, this is a type 1 error, okay? Here we have rejected the null. We have concluded the smoke detector has concluded there is a fire, but in fact, there was no fire. In fact, the null hypothesis was true. And the type 2 error is the reverse, okay, or not the reverse, but the other situation where the reality is that there is a fire, but the smoke detector concludes there is no fire, and that's also a bad thing, okay? All right, so which error is worse? Type 2 error, right? Type 1 error is annoying, but type 2 error is potentially tragic. So type 2 error is worse. And so in that situation, would we want a large alpha or a small alpha?
Large alpha.
Yeah,
Increase beta?
exactly. We want a large alpha. Okay, so we choose large alpha, meaning we will we make our smoke detectors sensitive, so that, you know, if you burn your toast, it'll set off the smoke alarm. Okay, and there's a little, it's a little reassuring when that happens, right? Because if the smoke alarm goes off when you burn toast, you know, oh, okay, well, it'll at least warn me when there is a real fire. Okay, and I think it's probably be a little bit alarming if your toast catches on fire in the kitchen or something and the nearby smoke alarm doesn't go off. You'd say, I wonder if this thing actually works. So the type 2 error is worse. We choose a large alpha. We make our smoke detectors sensitive. Okay. All right. I'll just tell you a situation where the opposite is better, okay? I was going to have you guys think of it, but I think it's kind of hard. Or I don't know, maybe can you guys think of a situation where we would want a small alpha where type 1 error is worse than type 2? So we're going to do a criminal trial. Okay. And so in the criminal trial, we look at our defendant and we say, we always presume what?
Innocence.
We presume innocence. So that will be our null hypothesis. Okay, so our null hypothesis is that the defendant is innocent. And the alternative is that the defendant is guilty. Okay, and so when we say the justice system works, that means guilty people are convicted, and innocent people are acquitted. So these are correct. This is examples of the justice system working. But we can have type 1 and type 2 errors also. Okay, we can have two types of mistakes. We don't want to make either mistake, but they happen. So what would a type 1 error be? We have rejected the null when the null is actually true.
Convicted a defendant when they're innocent?
Yeah, so type 1 error is convicting an innocent person. And a type 2 error would be,
Acquitting a guilty person.
yeah, acquitting a guilty person or letting a guilty person walk free. Now, we don't want to make either type of mistake, but with the way our justice system is set up in the US, what would we say is the worst mistake? Convicting an innocent person, right? We always, there's a little bit of a, which mistake is worse? And I would agree that convicting an innocent person is worse, because I think, a lot of high-profile cases, a lot of times end with acquittal, and we feel like there's injustice when people that we feel are guilty are let go. But I think there's something even more upsetting when we hear that an innocent person was convicted. Okay, I don't know if you guys listen to the Serial podcast. I think the great success. Well, it's very well produced, but it's a very compelling story because there's the question: did we convict an innocent person, or did the justice system convict an innocent person? Okay. And so in this case, we would say, and people might disagree, but I would generally say type 1 error is worse. Okay, and so in this case, we choose what? Large or small alpha? Small alpha, okay. Okay, and they actually tell you this in the courtroom. They don't actually say use a small alpha, but what do they say?
Beyond a reasonable doubt.
Beyond a reasonable doubt, okay? Because they don't want you to just convict someone because you've got a hunch or you've got a feeling or a suspicion. They want you to be certain beyond a reasonable doubt. So anything less than reasonable doubt, you are not supposed to convict. Okay, so anyway, this is kind of the theories behind rejecting or not rejecting. Oh my, it's already 8:20. Let's take a short break then.